Hey, welcome back to your favorite calculus class. We're going to talk about antiderivatives. Up to this point, we've studied how to find derivatives of function, applications for derivatives, but there's also other problems in calculus where we require that we recover a function from its known derivatives. For example, if you're talking about physics and you have, let's say, an acceleration of an object falling from an initial, or I'm sorry, you have an acceleration of an object falling from an initial height. We can use that to go backwards and find that velocity and its height at any time t, as long as we know how to take an antiderivative. So let's talk about antiderivatives here for a minute. A function f is an antiderivative of f on an interval if its derivative takes you back to the function. So for example, let's talk about 3x squared. What's the function? Who's the original function whose derivative gives you 3x squared? And you're probably thinking to yourself, x cubed. I know the derivative of x cubed is 3x squared. Now, is there another function you can think of besides x cubed whose derivative is 3x squared? If you think about that for a minute, you're like, well, if I just put any old constant on the end, when I take that derivative, it'll take me back to the function I was looking for, 3x squared. Of course, the derivative of 7 is 0. So, any of these derivatives, right? Any of these functions, when you take the derivative, you get 3x squared, right? So this is saying if the derivative is 3x squared, the antiderivative of 3x squared, here's how you note that. This is called the integral or the antiderivative. Antiderivative with respect to x, the antiderivative of 3x squared is x cubed. In other words, when we take the derivative of x cubed, we get 3x squared. And that's plus any constant. So here's the family of functions who, when I take the derivative, right, I could have x cubed minus 5, and I know its derivative is 3x squared. So here's the solution. The antiderivative of 3x squared is x cubed plus any constant. That's the antiderivative, right? Can you think of another one? Whose derivative is 2x? If you know that the derivative is 2x, who's the antiderivative? What function gives you 2x? In other words, if I take the integral, if I take the antiderivative of this, the antiderivative would be x squared plus any constant. Doesn't matter what this number is, because when I take this derivative, I get 2x. So the antiderivative. Well, these are differential equations. We've been expressing them as like dy dx. That's a differential equation. Y prime is 3x. This is another differential equation. Or x squared plus 1. Those are all where you have the differential equations. So let's say we've got dy dx, or y prime is 2. And I'm going to note this in a couple different ways. Y prime is 2. So if I run the antiderivative, I'll get back to the original function y, or y of x, right? So, and I'm going to add in a with respect to x here. So if I take the antiderivative of 2, so I'm thinking to myself, derivative of what gives me 2? Well, derivative of 2x. And it doesn't matter what this constant is. Anytime I take this derivative, I get 2, right? Derivative of 2x is 2. So the antiderivative is 2x. Now here's another way to express that with some other notation. Dy dx is 2. Take the dx over. So I have dy equals 2 dx, and I run the antiderivative. I run the integral, and that will give me my solution. So the y of x is 2x plus a constant. Notice again, if I take this derivative, again, this is just any old number. If I take this derivative, I get 2. All right. So here's the family of functions. The constant might be 2. Maybe this one's 2x plus 2, or maybe it's 0. 2x plus 0, or maybe the constant's -1. Unless they give you more information, you just leave it with a capital C. Okay. So again, this is just showing some notation that I've already introduced. If you take the dx over, you run the antiderivative here, and you have y equals whatever the antiderivative of f of x is plus a constant. Okay. So capital F of x this is saying the antiderivative of that. In other words, if I take the derivative of f, if I take this derivative, I get that original f of x in there. Okay. And these are referred to as indefinite integrals because we don't know what the constant c is, again, unless they give us some more information. So here's some more basic integration rules. We know the antiderivative. This is expressing I've taken the antiderivative and I have the answer over here. So the antiderivative will undo a derivative, right? So for example, if you have if you have a derivative in here already, but you're running the antiderivative on it, you just get of x. That's what this is right there. So it undoes it. If you run a derivative on an antiderivative, again, they undo each other, and so you're just left with f of x. We'll talk more about those as we move on. So here's some basic integration formulas. If you remember, the derivative of the constant is 0, so the antiderivative of 0 would be the constant. If the derivative of kx is just k, then the antiderivative of k would be kx, right? Again, k is just a constant. So the antiderivative of 1, for example, would be 1x, because I know plus a constant. Because I know if I take this derivative, I get 1. The antiderivative of 7 is 7x plus a constant, because if I take this derivative, I get 7. Right? Well, that constant k can be put out front of the derivative. When you're adding and subtracting, you can split them up. Take the antiderivative separately. And then here's the old power rule. We know the derivative power rule. So going the other way around, it would be x to the n plus 1 over n plus 1. For example, let's do it with 3x squared dx. And we know the antiderivative of that. Let's go ahead and take the antiderivative of that. We say, well, the derivative of what is 3x squared, and we know it's x cubed plus a constant, right? Because we know the derivative of x cubed is 3x squared, and then derivative of constant is 0, so you get the 3x squared right there. Well, let's do it with our rules now. I can put the 3 out front, so forget about that 3 for a minute. Oops, that's an x squared right there. And now this is saying I take it x to the n plus 1, so I leave the 3 there. I take it to the 2 plus 1 over 2 plus 1, and then plus a constant. So this ends up being 3 stays there, x to the 2 plus 1, so x to the third, and that's over 3, plus a constant. Well, the 3's cancel, so you got x cubed plus a constant. I say, oh, that's the antiderivative of 3x squared. The integral of 3x squared is x cubed, because I know if I take this derivative, I get 3x squared. Right? So now we have a rule for it. Don't forget that rule. By the way, throw a couple other rules in on this that we're going to use in this section. Throw that one in. The antiderivative a to the x dx is 1 over ln a to the x plus a constant. Well, they're both on your PDF sheet as well. Here's some more. You know, the derivative sign is cosine. So the antiderivative of the cosine would just be sine, because again, the derivative of sine gets you back to cosine. So notice the signs changed on those. You want to definitely remember those, right there, those 3 for sure. All right, so let's do the antiderivative of 3x. The antiderivative of 3x, yeah, with respect to x, put the 3 out front. I'm going to run the power rule. Right now, this is to the 1 power, so it's going to go up 1 plus 1 over 1 plus 1. And then plus a constant. So this is 3x squared all over 2 plus a constant. Notice if I take this derivative, I get back to 3x. So we're going to take the original integral. We're going to possibly rewrite it. We're going to run the integral with our rules. And then we're just going to clean it up, simplify it algebraically. Okay. All right, so the initial condition. So what if they give you an initial condition? So for example, let's do this right here. We have the integral of 3x squared minus 1 dx. 3 stays alone, x goes up a power, it's over that same number, minus 1, I tack on an x, and then plus a constant. So I got x cubed minus x plus a constant. So it could be any of these graphs that's shown right here, just depending on what the constant is. But if they tell us, hey, f of 2 is 4, so it goes through this point, f of 2 is 4, right? This is our antiderivative here. This is our antiderivative. We took the antiderivative. If they tell us it goes through the point 2, 4, then we know we can find that constant. You just plug it in. F of 2, which is 4, so plug in 2 for x. Oh, here's our constant, it's negative 2. So that's what our constant is. So the function is x cubed minus x, and then the constant is plus a negative 2 or a minus 2 on the end. So we know it's got to be this one because it goes through that 2, 4 right there. So, but they have to give you an initial condition. Otherwise, you just got to put a plus c on the end when you take the integral. Okay, here's another one. You got the derivative here is x to the negative 2 or 1 over x squared. Notice I rewrite that. So if I run the antiderivative, it's going to undo it and leave me with that f of x there. I'm doing this with respect to x. So now I'm going to go negative 2 plus 1 over negative 2 plus 1 plus a constant. So I got x to the negative 1 all over negative 1 plus a constant. Rewrite that properly. That's negative 1 over, that's just an x right there, plus a constant. Now I'm going to use the initial condition. It tells us, hey, this goes through the point 1, 0. So f of 1, which is 0, put the 1 in for x. Hey, our constant must be 1. That's our constant, so the function must be negative 1 over x plus 1 plus our constant. Oops, plus our constant. Oops, that's awful. There it is, negative 1 over x plus the 1. All right, we found what the constant, what the general capital C actually is. Now this one, we're taking the antiderivative 6 to the negative x, so we got to remember that you're using this rule here, which is 1 over ln a to the x plus a constant. Now the problem is if you have something besides just an x up here, right? If you have a composite function, okay, you can't just follow the rule. It's like with differentiation, right? We had with differentiation, we had that chain rule. Okay, similarly speaking with the antiderivative, except we have an approach that's called U substitution. Okay, so this is the substitution method. I'm introducing it to help you out with this section of homework because they introduce a few functions that apply with it. And we'll go into more depth with our substitution method later in the course. But just know if you have a composite function, right? This is not just integrating 6 to the x dx. That would be no problem. If I was doing 6 to the x dx, I'd just follow it. 1 over ln of 6, 6 to the x, plus a constant. This is 6 to a negative x, right? That again is the problem right there. This is f of g of x, where g of x is that negative x. It's a composite function. So what you do is you're going to let u be the g part, the inside part, that negative x, okay? And then you're going to take its derivative. So du dx, which we know is negative 1, but I'm going to take the dx over to the other side. Okay, so I have du is negative 1 dx. And what we're trying to do is we're trying to set it up so it fits this right here. Okay, and let me go ahead and erase this stuff here for a second. Okay, so we're trying to get it in this form. Integral of a to the x dx, 1 over ln of a to the x plus constant. Except we're doing it with u. Okay. Well, I've let u be negative x, so that's going to become a u right there. But what I need is I need negative 1 dx to be in this. So right now I have this, and I have dx, but I need negative 1 dx to replace it with a du. So I'm going to put that in, negative 1 dx, which means I got to offset it on the outside. So I'm going to put a negative 1 on the outside, because I know negative 1 times negative 1 is positive 1, so I'm not doing anything. All right, so I have a negative 1 right here and a dx. So there's my du, right? Negative 1 dx is du. So I make the replacement, and then that negative 1 stays on the outside. Now it fits the rule. Okay, u is my x, 6 is my a. So the negative 1, so I'm going to follow this. The negative 1 stays there. Let me write this right under it. 6 to the u du. So this becomes negative 1 stays there, right? That negative 1. And then I got 1 over ln of 6 to the u plus a constant. Multiply that negative 1 through, so I got negative 1 over ln of 6 to the u. And I can put the u back in now. U is negative x. So we were doing this with respect to x. And then negative 1 constant is just a minus a constant, or plus a negative constant. It's just a constant still, so you just leave a plus c on that. Okay, and that's how you do it with u substitution. Here's just a screenshot of those basic integration formulas that we have. Here's the one that we just used, except with u substitution. And again, don't forget this one as well. Add that to your list if you don't have it on there. Okay. All right, so you're looking at these, and you're looking at these, and you're thinking, well, okay, I'm gonna have to go back to this list here. It's got to fit one of these. So notice the 3 over square root of 1 minus x squared. 3 over square root of 1 minus x squared. So I'm like, it's going to be this one here. Does it fit this mold right there? So 1 over square root of a squared. Um, over square root of a squared minus u squared du. Right, so I'm following this right here. Is the arc sine of u over a plus a constant. Arc sine u over a plus a constant. Okay. So can we get this to look like that? Can we manipulate it? Well, I can push the 3 out front. That's no problem. So then I'll have the 1 over. And the 1, well, that's 1 squared. So my a is 1. And the x is my u. Minus x is my u. So again, a is 1. U is x. So I can follow it. No issues here. 3 stays in front. I follow the formula, so I have arc sine, so this becomes arc sine u, which is my x, over a, which is my 1, plus a constant. Distribute that. 3 arc sine of x over 1 plus 3 times the constant. Again, that's just a constant. You just leave it as 3. 3 times a constant, still just a capital C constant. Okay? Now let's do this one here. 1 square root, or I'm sorry, the integral 1 over 1 plus 36 x squared. Let me, you know what, I'm going to need some room on this. Let me erase this real quick. So now I'm looking for, all right, do I have one of these that's in this, that kind of fits this mold so I can manipulate this and do this integral here? And I'm like, oh, here we go, right there's one. Okay, that one is the one that we have to use. The integral of 1 over a squared plus u squared du is 1 over a arc tangent q over a Again, I'm using this number 17. 1 over a squared plus u squared du is 1 over a arctangent u over a. Arctangent u over a plus a constant. All right, so we got to get it in that form. I'm pretty close here. You know, I got the 1 squared. And then now the problem is this is not just x squared. It's 6x squared, right? That's 36x squared. So the problem is I've got a composite function. So if I got a composite function, here's another time we got to use the u substitution. We're going to have to let me write this down below here. If u is not just x, I got to let u be 6x and then make a substitution so it fits the rule. So I know du dx is 6, right? The derivative of u with respect to x is 6. I take the dx to the other side there. Okay, so du is 6 dx. So du is 6 dx. So what I need is I'm gonna first replace 6x with u. And then I need 6 dx. I have 1 dx. I need 6. So I'm going to go 6 times that. That'll be my 6 dx, but I got to offset the 6 because I've changed this integral. Offset it with 1/6 because I know 1/6 times 6 is just 6. Now I have 6 dx, which what is 6 dx? It's du, so I can put du in. And don't forget, you got to leave that 1/6 that you offset it with. All right. So then this becomes 1/6, and now I can follow the rule. 1/6, so 1 over a. This is my a, and this is my, well, my u is the u, but I'm going to make it 6x in a minute. So 1 over a arctangent of u over a plus a constant, and distribute this. So 1/6 times 1 is just a 1/6 arctangent. Now I'm going to put the u back. What is u? Remember, u was 6x, so this is 6x over 1 plus, and then I got 1/6 times a constant, which is, again, it's just a constant. You don't need to put 1/6. So 1/6 arctangent is 6x plus a constant. Solution on that one. There's our solutions there. Let's do another differential equation here, a couple more differential equations. So dy dx is negative x. So dy dx is negative x. I'm going to take this dx over. So dy is negative x dx. I'm going to run this integral. The integral of 1 with respect to y is 1y. 1y. And I know, by the way, I know this is plus a constant, but when I do it over here, you know, negative stays there, take it up a degree and put it over that same number plus a constant. You know, this constant different than that constant, but when I subtract these constants, all I care about is I have a constant right there. So that y is negative x squared over 2 plus a constant, right? So that's why we don't do the little plus the c over here. We just tack it on to one side when we run that integral, okay? All right, so we got y equals negative x squared over 2 plus constant, but they do give us an initial value here. Y is 1 when x is negative 1. So I got negative 1 squared over 2 plus a constant. So I got negative, that's a half. I add the half, right? Add the half, add the half. So it looks like 3 halves is our constant. So that's our constant. So the y must be negative x squared over 2 plus 3 halves, right? So it's got to be that one, right? We got a quadratic flipped over there and bumped up a little bit. So, and it goes through that point, negative 1, 1. Here's another initial value problem. This time, though, it looks like we have a second derivative. So if we have a second derivative is negative 6x plus 2, when I run the integral, then I'll just have the first derivative, right? So let's run the integral, negative 6x squared over 2 plus 2x. plus a constant. So here's my derivative. And then they say, hey, I'm giving you two values here. The first derivative at 0, y prime at 0 is 4. So let's let 0 go in for x. That's gone, that's gone. Looks like our constant is 4, right? That's what our constant is. So y prime of x is negative 3x squared plus 2x plus our constant, which we now know is 4. We're going to run the integral again to get to our original function y of x because it undoes the derivative. Negative 3 stays there, x goes up a power over that number, 2 stays there, x goes up a power over that number, 4, add on the x. Don't forget this is plus a constant. We got y of x is negative x cubed plus x squared plus 4x plus our constant. And now we're going to use this initial value, y of 0 equals 1. Y of 0 is 1. So again, let x be 0. Those are gone. Our constant is 1. This constant is 1. So y of x is negative x cubed plus x squared plus 4x plus 1. There is the solution to our initial value problem when we're given a second derivative, right? We had to take the integral twice to get back to the original function. Well, thanks for listening. I hope this will help out with your homework. You can kind of make sense of these antiderivatives or integrals. We'll work some more on this stuff uh, later in this course as well. Bye-bye.